Hello everyone, welcome to my YouTube channel. We discuss about a SC205 project, graph theory used in transportation problems and railway networks. Move towards the next abstract part. This model give an idea about how graph theory used in optimization and reduction of cost and time in transportation railway systems. We discussed below there are type of graphs and information that are used specifically railroad systems in graph theory and problem in railway system and some applications. Let us move towards the introduction part. We use graph theory in many researchers. It helps researchers to research of provable techniques in discrete mathematics. The graph theory is explored in many applications in computing, industry, natural science, and social science. In the history of transportation and telecommunication, graph theory networks have played a significant role. Additionally, there are specific graphs and information types utilized in graph theory for railway systems. In application, there are three London Underground train lines are converted into graphs. Each is examined in relation to one of the design and safety issues with the railroad system. Third, there are three problems: blocking problems, yard location problem, and train schedule problem. We will focus on yard location problem mainly, and we saw one more problem is Chinese postman problem. So before we move towards the type of graphs. Type of graph, there are three different form of graphs: weighted graphs, directed graphs, and double vertex graph. Let us move toward the first one, weighted graphs. Each edge denoted by T and weight, such as the separation between the two vertices. The shortest and most effective path to take can be found using weighted graphs. Two well-known examples are Chinese postman problem and traveling salesman problem. Our main focus is Chinese postman problem. We saw one or more example on traveling salesman problem, but we saw algorithm and all solution of Chinese postman problem. Let us move towards the example. This example will be a version of the traveling salesman problem. Consider a graph P with the following vertices and edges. Imagine that P represent a route where P, Q, R, S are different cities. Let us see the figure. P, Q, R, and S different cities. And each edge connecting to city represents the total length between the two cities. Suppose we take P and S, the total length between two cities is 5. Okay, so let us move to the next part. For example, between C and P, two cities difference is 9 kilometers. A person has to travel from city P and visit every other city once and return back to city P. What is the shortest route in this possibly take? So there are six routes as mentioned above figure: P, Q, RSP, PQ, SRP, PR, QSP, PR, SQP, PS, QRP, PS, RQP. There are six routes. And the shortest one is the first one and last one. Means PQRSP and PSRQP. Okay. So both are 39 kilometers. Additionally, this circuit would also be considered as Hamiltonian circuits. We can build railway system using a data and graphs like, but there are more effective graphs that consider every aspect of a railway system. Note that this version of the problem was inspired by two examples: Chinese postman problem and traveling salesman problem. As a result, we can observe that some graphs have edges that can be traversed in both ways, indicating the edges do not have a defined direction. And edge that can be traveled upon in both directions is denoted pictorially as a single line in a graph. So let us move towards the second one is directed graphs. So directed graphs D is finite, non-empty, and the set of vertices. Together with some directed graph edges joining the pair of vertices, it can be said that the edge endpoint function associated to each edge T to an ordered pair of vertices V and W, where V is the initial vertex and W is the terminal vertex. Terminal vertex means ending vertex. and initial vertex means starting vertex. Directed graph are held to additional restriction. The initial and terminal vertex cannot be same. A single line with an arrow can be drawn and edge must be only traversed in a one direction. Let us take one example. Consider this graph. This graph has one direction. Let's take C1 and C2. So direction is must be in traversed in one direction. Okay. In order to complete a circuit that starts and ends at C1, we can only perform the following circuit as C1 T1, C2 T2, C3 T, C1. This is the only circuit starting and ending at C1 because of directed edges. Okay. Let us consider one more example. Consider beside graph. If we want to complete a circuit with starting and ending at C1 days, we will have to do following two circuits. Okay. Circuit 1 and circuit 2. Therefore, since there are no directed edges, we can make a circuit by starting from C1 to T1 days and C1 to T3 days. Okay. Notably, there are some edges that are directed and some that are not directed, so directed graphs. Okay. The edges that can only be travels in one direction are always be indicated by an arrow. And undirected edges can be presumed to exist at that edges that are not indicated by an arrow. Okay. Let us move to the next part. Is a example, another example. Consider this graph. So in this graph, we can see that E2, E3, E4, and E6. These are not considered as directed because not given arrow. Okay. So travel upon in both direction. Okay. And E1 and E5, this is I mark in red figure. Okay. Red marker. E1 and E5 are directed edges. When applied to the railroad system, we can have a train tracks that are only traveled upon in one direction, while there are other tracks that can be traveled upon in both directions. Okay. Let us move towards the next part. Is a double vertex graph, is a last one graph category. In a railroad system, we must take into account more than track's lengths or the direction that train goes in order to make decision. For example, we must consider the speed of a train given track. Is a graph, weighted graph, directed graph of the railway system alone would not contain the specific physical information about double vertex graph of the railway system does. So let us move to the next part of the definition part. Let a double vertex graph tree be a finite non-empty set of vertices V of G. There will be finite set of edges E of G between the vertices, where none of the edges are loop or there are multiple edges between the pair of vertices. Additionally, these graphs are specifically for railroad system and every edge holds different piece of information for the railroad, such as track length, maximum speed, etc. Let us move towards the design and safety problem in the railroad system. The design of railway system must take into consideration of a number of safety and design issues because certain trains can only run in one direction, but the use of two-way line railway road system needs to be properly built. Therefore, it is important to prevent train accidents because if nothing is done to consider for the fact that two trains will be traveling on the same rail at same time, it is possible that may have collide. We will focusing on two problem mainly. The first one is Chinese postman problem and second one is yard location problem. Okay, let us move towards the next one. So, so that is the Chinese postman problem. In 1962, a Chinese mathematician called Yuan Maiko was interested in postman delivering mail to a number of streets, such that the total distance walked by the postman was as short as possible. How could be the postman ensure that the distance was minimum? So that was our first goal in Chinese postman problem. We will see that solution before we move second problem. Second problem is yard location problem. We try to find the best network configuration in terms of number and the location of yard where car can be reclassified into new blocks and switch trains. The train travel to a yard on its way from its departure location. which we shall refer to as origin, to its final destination, as was previously stated. Trains from other train lines in the system are classed in yard before being sent to a different locations. Local yard, system yards, and regional yards are the three different categories of yards. Local yard are used when trains are arriving from stations that are divided into blocks but are not in yards. System yard and regional yard are regarded as hub yard as they both handle larger quantity of trains and commodities. Compared to system yard and regional yard, local yard are smaller. So let us move to the next. Additionally, the goal of the yard location problem is to reduce the total distance of the train journeys, much like the blocking problem. Okay. Due to the growing traffic on railroads and addition of more trains, even if the blocking network is minimized, we cannot accurately minimize the path of the train if the number of position of yard are not taken into account. We can calculate a more precise minimized path of our train from its origin to its destination by taking in account both the blocking network and the yard in a railroad systems. Let us move towards the next part is the application part. An application part we saw first solution of the Chinese postman problem, and secondly we saw yard location problem solution. Okay. So Chinese postman problem solution. A postman has to start with A, walk along 13th Street and return to A. The number on each edge represents a length in meters. The problem is to find a train that uses all the edges of the graph with minimum length. Okay. So let us move towards the next part. That is the figure of this Chinese postman problem. Okay. So in this figure, we learn few things. We will look at make it different graph first, then we will get back to the solving actual problem. The graph below can be used to negative edge the Chinese postman problem. Okay. So drawing graph 1 requires removing pen of the pages retracing the page. So we can draw graph 2 but only starting at either A or D. In each case, path will be end at the other vertex of D or A. Graph 3 can be drawn regardless of starting position and you will always return to a start vertex. Okay. So we following the figure in the previous slide. Graph 1 is vertex A has order 3, B has order 3, C has order 3 and D has order 3. Okay. In graph 2, A has order 3, B has order 4 and C has order 4 and D has order 3 and E has order 2. In graph 3, A, B, C, D have order 4 and EF is order 2. Okay. So we generalize the result that can be said is the graph is traversable if all the vertices are arranged in even numbers. So we can draw the graph when there are two odd vertices but the start and end vertices are different. That is the first one and that is the second. Okay. And third one is said that the graph cannot be drawn when there are four odd vertices without repeating angles. Okay. This is the third one. So from this result, we can use this result in Chinese Postman algorithm. An algorithm is finding optimal Chinese route is step one we take is list all odd vertices. Step two we'll take is list all possible pairing of odd vertices. Step three is for each pairing find the edges that connect the vertices with the minimum weight. Step four is find the pairing such that sum of the weight is minimized. Okay. So let us move towards the next is step 5. Step 5 is original graph edits that have been found in step 4. Okay. The length of optimal Chinese postman route is sum of the whole edges that can be found in step 4. Okay. And a route corresponding to this minimum weight can be easily found. Okay. So application of the algorithm in the following figure is like this figure we can say all the thing. Okay. So first step, list all odd vertices. Okay. So odd vertices, we can see that only two have odd vertices like A and H. Okay. That's it. A has odd vertices 3 and H has odd vertices 3. Okay. So the optimal path is like A to H. Okay. So A to H minimum distance covered by this A to H is A to firstly we go A to B, and secondly this we go A to F, and then we go F to H. So total distance is 50 plus 50 plus 60 means 160. Okay, 160. And secondly, the whole total is around this figure. Whole total all vertices sum is around we take uh, 840 meter. Okay. So total is Chinese postman route to optimal Chinese postman route is 100 meter. Okay. So step one we see odd vertices A and H. Step two we see there is a one way of pairing like AH. And third we see A to H. The shortest path is 160. Okay. Step four figure. And step five we add 160 and plus 840 means Chinese postman route is 100 meter. Okay. The one possible corresponding route is like, for example, ADC, GHC, ABD, FBE, FH, FBA. But many other possible route, the sum minimum length can be found. Okay. So let us take one more example of this Chinese postman theorem. So find the Chinese postman optimal route. Okay. Let us see this example. This example we need to find Chinese postman optimal route. Okay. So what is the minimum this optimal distance by this theorem? Okay. So firstly, we can say that in this figure, A has 2 degree, B has 3 degree, F has 3 degree, G has 2 degree, H has 5 degree, I has 2 degree, D has 4 degree, and C has 3 degree, E has 4 degree. So odd vertices are 3 or ये odd vertices are H, odd vertices are C. So there are 1, 2, 3, and 4. Okay, 4 B, F, H, and C. 4 vertices are odd. Okay, so odd vertices, and we need to find solution. Let us move to the next slide. So next slide we show odd vertices are B, C, F, and H from step 2, step 3, and step 3. Above Malcolm we have draw one figure. Okay. So let us take in this figure, we show some applications. B has, okay, B, C, F, H has odd vertices. So distance between this, we previously slide, we saw that in step 3 and step 4, the distance between these vertices are minimum. So minimum distance between B and C is 120. Okay. So we figure out C and F 170 and F and H is 160. Okay. B and H is 90 and B and F is 50 and C and H is 1110. Okay. So we draw a graph joining this all four vertices. Okay. So this graph we show. In the next step, to move towards the next slide. Another figure. So possibly we have three paths. Okay. Possibly we have three paths. In this way, we move towards BF to we fix B. We fixed phi in previous figure. The distance is 50. Okay. Then we select a path that all vertices are included. Okay. Then one path only be remained is CH is 1110. Secondly, we select B is fixed. So we take a BC path. Okay. And BC path, we have distance 120. Okay. The second one is we need to all vertices included. So we select FH. FH is 60. And path 3 we B fix means graph means path is BH. So firstly we select BH and all vertices are coming included. Okay. So we take another path is CF 170. So total is 160, 100 and 110, 120 plus 60, 180 and 260. So in these three scenarios, we have optimal distance is 160 and we go towards the path 1. Okay. So we can say that optimal distance from path 1 and the distance is 160. These edges can be network in figure. We show this figure optimal path using this odd figure have this path. Okay. Path is BF and CH. Okay. So let us move towards the next slide. So specifically the wall length of the edges that original network sums up the length of the optimal Chinese postman route is okay. The optimal Chinese postman route is 150-meter long, which is equal to 89-meter plus solution step 5 is 160-meter. Okay. So we have cleared this Chinese postman problem. Let us move towards the second one, London Underground system. Okay. We will use the London Underground, sometimes known as the tube, to apply the graph theory to the design and safety elements of the railway systems. Okay. There are 11 There are 11 train lines in the Underground, which spans 250 miles. The Central Line, the Piccadilly Line, and the Circle Line will be specifically examined. Each line will be related to one of the three design of the safety problem issue, the rail system, the blocking problem, the yard location problem, and the train route problem. We will focus on the yard location problem. Okay. We will show only yard location problem. Let us move to the next slide. This is the figure of a London Underground system, which can be we saw that. Okay. Let us move to the next one. So next one is Piccadilly line. Okay. We will now talk about the Piccadilly line and the issue with the yard location problem. That is the solution of yard location problem. The Piccadilly line has 53 stations and travel a distance of around 44 miles. For a visual illustration, Piccadilly line see the following figure. Okay. So this figure is supposed to be one V28 starting and ending at E55 and one is starting from V1 and ending at V55. Okay. Let us do. There are 55 vertices of the 53 which are station colored black with the expectation of V30 which is colored blue. Since V30 is a merging point and a station where the train joins a new track to reach the destination of V5. The definition of merging point is a station where the train joins a new track to each destination V5. Okay. And two other vertices V55 is the final destination. Okay. There are two merging points in red. Keep in mind that the graph overall word directed graph. Okay. Component is created by two merging point. Consequently, there are word directed graph portion. Okay. V1 E1, V2 E2, V3 E3, V5 E5. Okay, V5, E4, V4, E5, V2. However, this area of train station is now closed and inaccessible as of 2021. Once more, we will assume that there are two trains. Train 1 which departs from station V28 and arrive at station V55. Train 2 which departs from station V1 and arrives at station V55. Keep in mind train 1 and train 2 are moving at the same speed. Okay. Let us move towards the next part. Consequently, we can determine subsequent flow. Train 1 has V28, E28, V77, V27, V30, E29, V53, E54, V54, E55, V55. Okay. And second part is this. Okay. Moreover, to see the Piccadilly line as a network system, dead block traffic. The Piccadilly line's blocking network system is shown in this figure. Okay. Starting our train 1 is V28 and starting second train is V1. Okay. So then we move into V25 and we move into V30. Okay. Then we will move it V55. So there is a junction type space. Okay. V25 and V30. Okay. Let us move toward the next slide. The blue dotted box highlights are origin nodes. We can see in previous slide V28 and the yellow dotted box the yard nodes. Okay, V25 and V30, and that both train passes to before arriving at final destination. So that is the yard nodes. Okay, or the station where T1 turns V55 and purple dotted box destination nodes. So purple dotted box are destination nodes of both trains. Okay. Overall, it depicts local yard. If we were to consider the whole London Underground, that would be a system yard. Note that another train line in the London Underground District line also visit V30. If we were refer back to the our figure and add that connection from district line, if we would like the following figure. So we would like to following figure. We add district line. So district line supposedly D1 and move towards the V30 and move towards to D2. Okay. Let us move toward the next slide. The district line train represented by D1, and D1 is origin node and D2 is destination node. To distinguish between the two separate blocking systems, the Piccadilly line blocking system and the district blocking system, they were depicted in blue. Three trains via V30 can be seen from the blocking network because all of the train must move in a certain speed. To avoid colliding with the one or another two, how far in advance they must stop if they are going to arrive at the same station at same time. It is crucial to example the overlapping blocking systems and particular the yard nodes in the blocking systems. Okay, let us move to the next. In order to from train T1 to travel V28 to V5, it takes approximately 1 hour and 41 minutes. Specifically, it takes 37 minutes to travel from V28 to V30. In order for train 2 travel from V1 to V55, it takes 1 hour and 33 minutes, and specifically it takes 29 minutes to travel V1 to V30. Lastly, it takes D1 6 minutes to travel from D1 to V30. By just looking graphically Piccadilly line, we can only view at the Piccadilly line and the Piccadilly line blocking network by simply glancing at figure. We can see overall that it is unlikely that three trains could be collide because there is a less space station between D1 and V30, where we combine some of discrete line blocking system with the Piccadilly line blocking system, particularly its yard node, together with the time information. Despite of the relative accuracy of arrival and departure schedules, train might become stop or break down at a station. As a result, in addition, looking at the yard of other lines, blocking network that could be impacted, we need to analyze the blocking networks of many train lines. Okay. So we move towards the conclusion part. When designing a railway system, especially in terms of safety using graph theory in the effective technique, we see Chinese postman problem and its solution. To find most optimal Chinese problem route, we created a graph of a train line in the London Underground, specifically Piccadilly line utilizing the fundamental characteristics of graph theory. In this slide, we were able to apply one of the design of safety problem, yard location problem. Overall, the basic and complex property in graph theory can be utilized and analyzed for design and safety problem in the railroad system. So our group members are firstly Part Doloria, secondly Avi Detroja, Priyank Ramani, Harsh Gajjar, Harsh Murukia, and Mayank Parmar. So thank you so much for this